All right, good morning, everyone. We're the mechanical engineering team, number 13. We're the Schramm drill transportation device. I'm the team leader, Anthony DiLuigi. With me is Mike Malason, we have Dion, Dixon, Anthony Schwarc, Mike Barrett, and our faculty advisors, Dr. Christopher Massey. Our industry advisors from Schramm Incorporated are Michael Horchuck and Larry Wiler, and our project coordinators, Professor Victor Marcus. So here's a quick outline of what I'm going to be telling you about. We're going to start with the objectives and constraints on our project. I'll tell you a little bit about the research that we've done, and then how we developed our final design from that, and then go over some analysis that we've done on that, and then tell you a little bit about the project management before we wrap it up with the conclusion. So what is the Schramm and a Schramm drill transportation device? Schramm Incorporated is a manufacturer and designer of drilling rigs located in Westchester, PA, and our team acted as a consulting firm to Schramm, where our main goal was to design all the necessary equipment to transport a drilling rig mast from one building to another in various locations on Schramm's facility. So, as you can see in the picture on the top left there, that's a completed drilling rig assembly with a mast standing vertically that Schramm has designed before. They're currently designing a brand new drilling rig with a much larger mast than anything they've ever done before. On the top right, you can see a drilling rig mast which is laid down horizontally, which is how we're going to be carrying it around. And this one is approximately 40 feet long. The one they're designing now is going to be up to 75 feet long and weigh up to 160,000 pounds. So keep in mind that's about double the weight of a standard tractor trailer. On the bottom left, you can see an example of a previously used running gear, which is the transportation equipment that we'll be calling. Again, it was built for a much smaller capacity, a much smaller size mast. On the bottom right is an airport tugger. This is one example of some sort of tugger that's going to be towing around our running gear to move the mast from one building to another. So some of the constraints on our project, like I mentioned, the size of the mast is one big constraint, plus the facility constraints. Doorways are only 13 feet wide in the buildings at Schramm, so we need to be able to fit inside of the buildings. We also can't break any asphalt as we're moving the mast around, as that's most of Schramm's facility, so we need to be careful with the weight distribution of our running gear. Also, we have to be able to swing around certain corners and be steerable enough to move between certain buildings. We're also working with information constraints. Like I said, Schramm engineers are still designing this brand new drilling rig. We were expecting final mast designs about 2 to 3 months into the project, but due to scheduling delays, Schramm still has not given us those final designs, and they haven't exactly picked a final tugger yet. So there are some information constraints that we're working with. Here's Schramm's facility laid out. You can see starting in building A is where the mast will start out. That's the machine shop. We're going to take the drilling rig mast from building A up a hill onto building B. We're going to need to do more assembly there, turn it back around, come back down the hill and into building C for some final assembly work. So as you can see, there are a lot of tight corners to maneuver around, and that's one of our bigger constraints. And right now I'm going to pass it off to Mike for some research.
Okay, so before we could arrive at our initial design, we decided we needed to do further research in these areas. The first area is that of casters. So what are casters? Casters are essentially the wheels that are on the bottom of shopping carts. The next area is that of turning and steering mechanics due to the maneuverability constraints throughout Schramm's facility. The next area is that of bearings and bushings. Because we have a lot of rotating machinery in our running gear, bearings and bushings can help reduce friction between metal and metal surfaces. The next area is that of fixture methods, when to use bolts and when to use welds. And the final area is that of finite element analysis, which will allow us to identify any points of concern in our final design. So this is our initial design. As you can see, we applied swivel casters for the front running gear and rigid casters in the rear running gear, much like the shopping cart example that I spoke about. One main consideration we had to make with this design was the load bearing for the swivel casters. The swivel casters had a rated load capacity. However, we were concerned that they would not be able to turn efficiently when bearing the load of the mast on. And the other consideration is that of maneuverability throughout Schramm's facility. We were concerned that when encountering inclines, you wouldn't be able to, the weight of the mast would not be evenly distributed on all of the wheels. So due to this problem of the incline, we decided to implement an I-beam right above the main axle pin. This I-beam will allow the weight to be distributed over all the wheels effectively, even when encountering those inclines. And there you see the I-beam above the main axle pin. Now I'm going to pass it on to Dion to talk about final design.
Our final design was based on that of a tractor trailer due to its maneuverability under heavy loading. If you look in the upper right corner, you can see our wireframe mast supported by our 2 running gear. The only difference between our front and rear running gear is the addition of the 5th wheel on our front running gear. Under that image is a larger zoomed in picture one of the running gear with the 5th wheel attached. A fifth wheel is seen on tractor trailers, and what it does is it couples the truck to the trailer and creates a point of rotation in between them during their towing. Also, the I-beam and center pin taken from the previous design was put into our final design to deal with the inclines, which Mike mentioned previously. The rotating main pin also allows for load distribution throughout the wheels. Bearings and bushings were both used in our final design. The wheels came pre-manufactured with bearings, and bushings were installed in the ends of the wheel axles, as well as through each flange which supports our center pin, just to avoid metal-on-metal grinding. And now I have a 3D model of our running gear for you. As you can see, it's separated into two skates, which is the left 4 set of wheels on the right and the other set of wheels on the left. As this image starts to rotate upside down, you can see the flanges which run under the I-beam that distribute the load to our wheels. The next image I have for you is of an assembly of one of our skates. As it starts to come apart, you can see the pin and axle caps coming off, followed by the block housing, which houses our thrust washers, which prevents shifting of the axle and center pin during movement. Next comes off one of those bushings that I said avoids grinding with metal on metal. This front plate coming off is just for stability purposes to prevent the side plates from shifting during travel. And the plate coming off to the side distributes the load from the center pin to our wheels. And as you can see, that plate also has bushings built in. And you can also see a better view of our bushings within each flange of our wheels. And now I'm going to pass it on to Anthony to talk about our analysis.
In order to ensure that our design would withstand the load of the mast applied, some analysis had to be performed. Theoretical stress analysis, experimental load testing, as well as finite element analysis were all used in different portions of the design. Shown here is a free body diagram and moment diagram of our main support pin. We treated this main support pin as if it was in pure bending due to the bearings and bushings minimizing rotation of this pin. The maximum moment was found using the moment diagram and used in the equations on the right to come up with the maximum shear stress. We used this shear stress to come up with a minimum pin diameter for the main support pin. We came up with a final pin diameter of 4 inches with an included safety factor of 5. Similarly shown here is a free body diagram and moment diagram for our wheel axle. Though the moment is much lower, resulting in a lower shear stress, we decided to go with a 4-inch pin diameter with an included safety factor of 10. We are also going to do experimental static loading tests on a scale version of the wheel axle. It represents 1/2 of the loading pattern that the wheel axle will be performed under. Unfortunately, due to technical problems with the testing machine, results couldn't be obtained for the presentation today, though testing is scheduled for next week, and results will be given to Schramm for their final design analysis. I will now turn it over to Mike to talk about the finite element analysis performed.
So following all of the theoretical analysis, we then simulated the stresses that would be being applied to both the wheel axle and the hitch pin. So as you see here, we first modeled the wheel axle as highlighted in the 3D model, and distributed loads were applied over the top surface over angles of 30 degrees ranging to 180 degrees, represented by alpha in the figure in the top right. And there were 2 surface boundary conditions applied at the same angles of the force to represent the wheels as supports. And we used a section view, as you see in the video being displayed, to properly analyze for any internal stresses that may have been occurring. And the maximum stress displayed in the red areas forming in the video was 5,093 psi. And when compared to the theoretical calculations, it only yielded a 1.6% difference, which led us to be very confident with our design moving forward. Now, the second finite element model was that of the hitch pin that will be connecting the tugger to the front set of running gear. And the tugger that we modeled is displayed in the left picture, and the distributed loads were applied according to the representation of the 3D model in the center. There were 4 loads totaling 80,000 pounds, as you can see on the right side of the model, coming from the tugger, and 3 reaction loads coming from the connection to our front running gear. There was also a boundary condition placed at location A, as you can see on the picture to the left, to represent the pin being stationary during tow. So the distributed loads, the maximum stress that occurred was approximately 19,700 psi, which was an acceptable level of stress that could be handled by our hitch pin design. So overall, the FEA allowed us to further validate our design before continuing to finalization. I'll now pass it back to Anthony for schedule, budget, and conclusion.
All right. As you can see here, our project began in September. We began immediately with research and conceptual design, which went hand in hand. After a few tweaks and tips and pointers from Schramm engineers, plus our own new ideas, we moved into our preliminary design phase. I want to point out again here, around December is when we expected final mast designs from the Schramm engineers of the mast. But again, due to scheduling difficulties, this got pushed back a little. But we continued with finite element analysis on the main portions of our design that wouldn't exactly be affected by not having that information yet. We eventually moved on to experimental testing, and you can see the little break in the experimental testing is where we had some problems with the testing fixtures. And then, as you can see, we have submitted a final design to Schramm, and it has been approved pending those experimental test results, which are expected to happen next week. So when it comes to budget and finances, this is brand new for Schramm as well as us. They've never done anything this big. They've never built mast this big or running gear. So we needed to look at previous designs to see what the costs were there and try and scale them up to reflect the characteristics of our proposed design. So our estimated costs were in the range of about $100,000. As the project went along, the wheels themselves cost over $30,000, plus the fifth wheel was, we have a quote over $5,000 for one of that capacity, plus all the labor and manufacturing costs for the rest of the running gear itself. So we still think we're in this estimated range of around $100,000. Schramm will be providing all the costs for the construction and manufacture of the running gear, and they'll follow the specs that we provided them in our design. So, in conclusion, these are a lot of the topics that we've learned so much more about during our project. Manufacturability and serviceability is the biggest one because whatever we design has to actually be built, and we need to be able to take it apart in case there's any sort of little product failure, and it needs to be serviceable. We learned so much more about steering mechanics because, like we said, maneuverability is a large constraint of this project, so we had to learn to move it around Schramm's facility as well as we could. We all took a class on finite element analysis specifically to be able to analyze the stresses better and the points of concern for our project. And we learned much more about mechanics and materials, which is classes we've had previously. And we learned much more about bearings and bushings because of all the pivoting and rotation involved in the running gear design. So I want to stress once again that our team has met all of Schramm's directives on time. We learned many new aspects about project management and how real projects come together. We were doing research in new areas not covered in the classroom, and we were working on a client schedule with information provided by a client. So, like I said before, our design has been submitted to and approved by Schramm, pending those experimental test results. And whenever a final mast design is completed by the Schramm engineers and a tugger is chosen, then attachment fixtures can be designed and finalized. So, I want to give some special acknowledgments and thanks to Dr. Nicosia, who helped us out a lot with the finite element analysis, and Rich in the machine shop for helping us out with all of our experimental testing. And I'd like to thank you all for your time. Once again, we're the Schramm dual transportation device, and I'd like to open up the floor to any questions. So is there anyone who has any questions?
Yes, for maneuverability, do you consider like the steerable back wheels?
We considered that, but we weren't sure exactly. There's such a large gap between the front set of running gear and the rear set. If we were going to attach them in some way and make it four-wheel steering, we thought it would be much better to just model it more similarly for a tractor trailer.
What type of lubricant have you specified for your bearing housings?
Excuse me?
What type of lubricant have you specified for the bearing housings?
We haven't specified that specifically, but we're talking to Pacific bearing providers, and we'll use whatever they recommend for the bearings that we purchase from them.
What type of test are you going to conduct next week?
It's an experimental scale test of the axle. We're going to load it in scale, and it represents one half of the pattern. We have strain gauges applied that will try to tell us if our experimental stresses match up with what we theoretically did and through our finite element analysis.
Is it?
I heard somebody mention a safety factor of 10. Could we go over the reasoning for picking such a high safety factor?
Well, we did that mostly because it wouldn't affect the cost too much. We were able to go to a much larger shaft diameter, and when it comes to the actual cost of the entire running gear project, it's minimal compared to the added safety because, again, this is completely new. They've never done this before, so there might be unforeseen consequences, and we'd like to jump the safety factor as high as we can while staying under a reasonable budget.
He's on the second.
What kind of roadway analysis did you do? Roadway percent you're
The Schramm contracted a civil engineer to come and test the asphalt, and they made sure that as long as a certain amount of weight wasn't applied over a certain width of the wheel, that the asphalt will be okay. I believe they gave us a maximum temperature that we were allowed to move the running gear over. I'm not sure the exact numbers, but that was on Schramm's end.
Do you have an idea of $100,000 if there's a business case to support that? Schramm?
They gave us a rough estimate of that, and they said if you can keep it in this range, that's okay. But again, there were no hard budget numbers coming through.
So do you think you'd be running down an optimization path?
Potentially, if we come back to them and say that safety factor of 10, and they say that the cost is actually a problem, we might need to lower that safety factor a little bit.
My assumption is that they're going to be fabricating more than one roadway. That's why they're not, like running a gold hopper.
Right.
And that's why you're designing this so they can have it on site for all future work that they do.
Right.
Are there any other questions? Thank you very much.